displacement, speed. We can do average speed, instantaneous speed, average velocity, instantaneous velocity, and then acceleration, which will, did I put both? I did.
There's a lot of space between the distance and displacement and average speed.
Yeah.
If you wanna.
There. Cool. Alright. Yeah. We're going to. No, we'll come to that when it comes. Okay. Cool. Alright, so distance travelled for purple.
3 meters.
3 meters. Actually, let's go around the room. Go on. Zach, displacement for purple. Where did it start?
1. So 0.
0. So,
Yeah, 3.
sorry, there we go. Beautiful. Dean, average speed.
3 meters a second.
Beautiful. Tyler.
That also be 3 meters a second?
Sorry.
That also be 3 meters a second?
Alright, so, if, do we know how this thing travelled?
Yes.
Do we?
Straight line.
No.
It travelled in a straight line, yeah, I'll give you that. But,
How do you know it travelled? You just know that it travelled 3 meters. You don't know if it was a straight line or not. You just know it took a second.
because of the, oh, okay. So,
Yeah, travelled at a constant rate.
so I'm assuming I've only got one dimension to play with in space. So
Oh,
I
okay.
only have an x dimension.
Yeah.
Or at the very least, we're only concerned about the x dimension. Right. If it went back and forth on the x dimension, then we've got things looping on itself to describe that.
Oh, I'm just saying if I went like this, that's like that.
Yeah, that's two, okay.
That's
Yeah,
3
yeah.
meters.
Yeah.
But I.
We're only concerned with one dimension of space.
Yeah.
Okay, fair point. Okay, which will say that dimension of x. Cool, okay. So, do we know how this thing travelled?
Straight.
Okay, travelled straight, totally agree. Does that tell us everything about how it could have travelled?
Travelled.
It couldn't
Yeah, positive
travel,
direction.
and we don't know if it traveled up, down, left, right.
If we only care about in the x direction.
You don't know if it went slow and then got fast later? Or
Perfect.
anything like that?
Is it possible that this thing went like that?
Yeah.
Yeah, right. Assuming that, like, I dragged that for a second, right? Is it possible that it went
Yes.
right? Is the instantaneous speed the same in those scenarios?
No.
No. If I go like that, is the instantaneous speed at every point along there the same?
Yes.
Yes. If I go, what's happening to the instantaneous speed?
It's accelerating.
Right, it's getting faster and faster, right? So this thing, we don't know. It depends.
No, lovely.
How would we get instantaneous speed?
Yeah, you pick a point.
We need a derivative of
Pick a point.
a point.
No, of the
Oh, of the equation.
What equation?
The from 0 to 1. The
Right, what kind of
y
equation would that be?
mx plus c. Right? Is it a straight line? No.
it'll be
mx plus c requires an x and a y.
Oh yeah.
Second.
Yeah.
Tx, almost. So, okay, one coordinate might be Tx, right? But what you want is all positions described across time, which would be x in terms of t. So,
Oh,
this position thing, that's one particular position, but you could have all positions would be some function of t, sorry, my bad, that should be x as a function of t. Right, so that describes all your positions over time. Okay? So this is one particular position in time, just one dot. This is all the dots. Go. So this thing, we'd need to get a derivative, right? And then we'd need to ask about one specific point in time. Oh, okay. Who's next? Jacob's not here next time? Or you are? I don't know. You know? Fletcher, staying or no? Yeah? Alright. Average velocity for purple.
3.
3. Cool. How do we get there?
Displacement over time.
Right, displacement over time. So 3 over 1, 3 meters per second. Talking about velocity. Cool. Tyler, instantaneous velocity.
You don't know.
Right, we can't do it. Why?
Because it could be.
Right, we don't have enough information, right? We need a function in order to get an instantaneous anything. We need a derivative. Cool. Who's next? Riley, average acceleration.
That just be 3 minutes per second.
Depends.
Come on, boys.
If I go like that, did I accelerate at all?
No.
If I go, did I accelerate at all?
Yeah.
So,
What?
what information do you need? More, yes.
The speed which you travel to specific points.
Almost. So to get an average acceleration,
The velocity.
right, you need the velocity at the start and at the end.
Yeah.
Yeah, and then you can take your average.
So
Or if it's varying throughout. So this stuff gets a bit more fiddly, right, without more information. Cool, okay. Little boy blue. Over the curve. Celestia, distance for blue.
3 meters.
Okay. Next. Gary, displacement. Almost. Which way is the arrow pointing? To the negative, so my displacement. Negative. Cool. So distance and displacement might be the same, but they might not be. Average speed for Mike. Say again. 3 meters per second. Average speed, yes. Cool. TJ,
You can't do.
can't do it, so give me the next thing.
Few meters per second.
Almost.
Negative.
Negative 3 meters per second. Alright. Cool. All these, we've got the same problem as before.
Wait,
Yep. Sure.
Why is it not positive and then negative?
Why is it not positive then negative?
Oh,
you
yeah, checks, I thought we were looking at green. That's why.
Oh, okay, that was good. All good? Beautiful.
I don't see it.
Brian, distance for green.
4 meters.
4 meters, fantastic. Aaron, displacement for green.
0.
0. No, I lost it. So green goes and back again.
Oh, grass, I was looking at red.
Everyone's colorblind, okay. Cool, back to the start. Zach, average speed. I don't know, okay. So how far has it travelled? Distance-wise. How far has it travelled? 4, right? How long did it take to do that? 2 seconds, therefore the average speed?
4 over 2.
2, right? 2 specifically meters per second. Cool, we don't have that. Dean, average velocity?
0.
0. Why is it 0?
It didn't move anyway.
Because, wait, it didn't move anywhere?
It didn't like displace anyway.
Okay, it didn't displace, right? The displacement was 0, right? And average velocity is displacement over time. Beautiful. Don't care about them, right? Tyler, 8 meters. 8 meters, 1 Yep. Next is Fletcher, displacement, 0.
4 meters per second.
Meters per second, that seems good. Yep. Riley,
0 meters per second.
yep. Next, Slicey,
4 meters.
1, 2, yep. Gary. 0, alright.
Who would have thought?
Do you know why it's 0 though? Right, starts and ends in the same spot, so displacement, 0. Cool, average speed, Michael?
2 meters per second.
Yep, I think so. Covers 4 and 2, yep. Cool, TJ?
0 meters per second.
Beautiful. Okay, now, I am going to impose something upon this, just for my own, okay.
So we figure
So,
out
instantaneous.
right. So, I am now going to say that these things all travel with no acceleration. They're all just at a consistent, whatever they're doing. Right, so whatever speed they start at, they stop at. Right, speed, not velocity equals speed. Okay. Based on that,
But just you.
Yep.
But wouldn't it be like at the point their acceleration would be 0? At the
not
starting
necessarily.
point?
This thing could have been going like this forever. And I've just started my watch here and ended my watch there.
Okay.
So this thing could have just been going, right? And I've only looked at this bit. Is that cool?
Yeah, that's fine.
But you're right, taking a derivative of an endpoint is like, what does that mean? Depends what the context is. But yeah, usually it's meaningless. Or commonly it's meaningless. Cool, alright. So I'm doing that. Could I now figure out an instantaneous velocity?
Yeah.
Yeah? Okay. For purple, is my instantaneous velocity the same everywhere?
No. Yeah.
Is it always moving in the same direction?
Yeah.
Did it ever accelerate?
No.
No, so must have been moving in the same velocity. Yeah, has to have the same velocity all the way through. What is that velocity?
5.
3 meters per second, right? Cool. Alright. If we go with blue, is it the same everywhere?
Yes.
Yes. So what's the instantaneous rate of change throughout all of blue?
Negative.
Negative, sorry.
It's going negative.
Yes.
It would
Okay. For green, is it the same everywhere?
no.
No. Okay, so now we have to think a little bit more carefully.
It's either positive or negative.
Right. So what I'm going to stipulate is that it constantly is the same this way, then it all of a sudden instantaneously changes and goes back the other way. Is that realistic? No, but I don't care.
You have to label the points and then give it.
Label points.
So you have to label where.
Let's call this M for midpoint then. M and N. And we'll call all the starts A's and all the ends B's. We'll do A, like that, cool? Just so we can describe the points without me constantly having to shuffle around and block you down. Okay, so from A to M, what is my instantaneous velocity all the way across there?
2 meters per second.
Yep. Perfect. Right, because that's half the trip. Took 1 second, we can travel 2 meters. Beautiful.
And B is
From-
negative.
No, not B, but M to B. So that entire trip is negative 2 meters per second.
Negative 2.7.
We okay with that? Cool. All right. For red, from A to M.
4 meters per second. 2 meters per second.
Right. Okay. How long does it take to get from A to M?
2.
1 second.
1 second. How far have you travelled?
Oh, yeah.
4.
4 meters per second.
We've
Yeah.
stipulated that this is a
Yeah.
nice smooth transition. Okay. So therefore, my instantaneous velocity across the interval A to M is a consistent 4 meters per second. Going from M to B, negative 4 meters per second. Cool. Now for the nice fiddly one. From A to M, my instantaneous velocity.
1 2/3 of a second.
Okay. How long does it take to get from A to M?
2/3 of a second. 2/3 of 2 seconds.
Half a second, hopefully.
Yeah, that's what I know.
Alright? Because we said that this thing's travelling at the same speed throughout. So, okay, it's travelled how many units in total?
We wanted 1.
Yeah.
40, right? Over 2 seconds. Okay, fine. So this thing has half a second to make the
Wait, is
first.
it half a
So
second?
it's 2 meters per second.
It's 2 seconds to go through the whole thing.
So it's 2 meters per second.
Right? So that's 1, 2, 3, 4 units that moved. Right? Half of that time is those two per second.
Ah, and then yeah, 0 force.
Yes. Cool, cool.
If it was 1 second, it'll be 140.
Say again.
So if it was if it's 1 second to go, that go through that whole.
Then it'd be a quarter, yeah. Wait, sorry. Wait, now we're upside down. So, yeah, sorry, it would be a quarter of a second, yes, sorry. Okay, so from A to M, what is my instantaneous velocity across that interval?
2 meters per second.
2 meters per second, right? Because it moved 1 meter in half a second, so it's 2 meters per second. Cool. Going from M to N,
2 meters per second.
Negative 2 meters per second. Going from N to B,
Positive 2 meters per second.
positive N. Go. Right. Is the math of this difficult? No. True, right? Is it easy to get tripped up with negatives and things like that? Yes. So this is more an exercise of don't be dumb than it is about be smart. Highly recommend, whenever you do anything, double check whenever anything like this comes up, because it's super easy to drop negatives, and just double check that, yeah, that goes this way, so that has to go that way. Beautiful. That's it. So that's 18F. The only other thing that it does is it will give you actual x of t functions, so that you can find what's going on. So, let's say x c is
M to N.
oops.
T squared.
So,
Yep.
why is M to N not 4?
Why is n to n not 4? Because we said this thing was always at the same speed, yeah? So the time that it takes to travel from there to there is the same as there to there. Yeah. So if it's got the same speed, the only thing that can be different about the velocity is positive negative.
Okay.
So
So
the
it's
velocity,
not distance that we're talking about.
it's not distance we're talking about.
Oh, these are done. So
Well, you could if you want so. There to there is half a second. Here to here is 1 full second. So I've travelled negative 2 meters in 1 full second, negative 2 meters per second. And then that's the last half second. Is that okay?
So then how did you get 2 meters per second for A to N?
Okay, so A to M, right? I've travelled 1 metre in half a second. 1 divided by a half.
What's 2? So why is it? Why does
so dumb.
the travel long distance?
No, they're so dumb because they're like, oh, we like to
So
make our
say
things so like
if you're moving at 100 km
they were, yeah,
right, how
worse
far,
now.
how far do you go in 1 hour?
There was one
Kilometers, right?
telling us,
Cool. You're travelling at 100 kilometers an hour and you
someone was
travel
telling us
for
we can't leave it
half
on.
an
I'm
hour,
going to
how far do you
say
go?
directly where we are. The other one was, another one said
Exact
I
same
had to
place
stay here.
that.
Everyone had to go here, the other one said you had to go
This one
there.
travels for
It's
half the
so,
time, so it only went half
like,
the distance.
like unfunctional.
They're travelling at the same speed though.
Oh, okay.
Yeah. You just gotta separate.
Yeah.
But this, it's not hard, it's just easy to conflate two different things.
So like it's like I'm traveling at 100 kilometers per hour, but I'm only traveling 50 kilometers, which means I'm only traveling 30 kilometers.
Dumbass.
Totally good. Alright.
No one had any.
Cool, so let's say we've got an object that's following that particular motion. So, we're going to do a couple of things that will be mildly upsetting, but you know. Okay, I want to know how quickly this object is, well, I want to describe this object's motion. Alright, I've got this function, but I want to try to describe it in words so I can get it in my head. What might be a good idea?
Draw it.
Draw it, right, draw it would be a good idea. How do I draw it? Factorize it.
Factorize it, right.
Right, okay, so
Oh,
what do I get when I factorize?
x equals negative 2.
T equals
Oh,
negative
sorry.
2.
Sorry,
How
x
did you make the
plus
mistake?
2x plus 4. Or x equals.
T.
Oh, sorry, t, sorry.
T equals minus
T
2.
equals 2.
And T
So we get
equals
that.
minus 4.
Beautiful. Okay, can I draw this thing?
Yes.
Yep, what does it look like?
Looks like a problem.
Looks like a parabola, specifically going through.
I'm going through
Points negative 2,
negative 2,
negative 4.
negative 4.
And then positive 8 for y. Bam. That's perfect.
That's terrible. But I'm happy with that.
Nice.
Cool. All right, we'll label off all these things. Is this graph to scale? Not even close.
10 plus 3 negative 2.
Right? That's something to keep in mind. It is not to scale, so just careful about how once you draw a line. Cool. Should I label anything else?
Turning point?
Turning point, choose.
Three, negative one.
-3, -1. Yeah.
Oh, sorry, that's alright.
Cool, cool. Everyone's happy so far.
It's literally in the negative quadrant, though. Like everything has to be negative. That's
No, you're all right.
Maths is dumb.
Everyone's happy with that. Brilliant. What are my axes?
X and Y. Oh, T and X.
T and X. Which one's which?
T is our.
T is going that way. X is going that way.
No.
Does that matter?
No. Oh, yes, yes.
Okay, so let me rephrase that.
Doesn't matter what they are. That
Right,
matters
okay.
which direction.
We're just naming these things, right? So
Yeah.
does it matter that now X is labelled as the vertical?
No.
No, right? But you have to now be careful about saying in the X direction or the X axis because that's changed. So just be careful about it. Okay. How is this object moving?
So it's moving straight, but it's going slow, very slow, and then it goes.
Okay, so we said it's moving, so TJ's saying it's moving straight but slow and then up.
Then very slow.
No, it's moving straight, but it's moving slow, very
Yeah.
slow. And then the acceleration increases and it
Okay.
just keeps going up.
Okay,
So
so
it just keeps going
you've
up.
got good bits in there but also
Oh, wait,
less good bits.
wait, hold on, sorry. It's starting at a constant speed, right? This is from like negative infinity or something.
Okay,
And then it goes gradually gets slower and slower and slower, and then it gradually increases getting slower, and then
gradually increases getting slower.
gradually decreases.
No, but that still doesn't.
That's
It just keeps getting slower and slower.
Okay, it gets slower and slower.
So it
That's
gets
good.
slower and slower, and then it starts a turn where it just stays at constant speed, and then goes faster and faster and faster, and then it gets faster.
That's it.
And now it's going up on the page apparently, with the way your hands moving.
It's getting.
Okay, let's
Yeah,
go back a bit. How many dimensions is this thing moving in?
2.
one.
One.
Alright.
Unless you want to count time as a dimension, which you can if you want, but we're gonna say in spatial terms, there's only one dimension being used. So, where is this thing at time? Well, let's actually put in some more points. 6, -5, Okay. Where is this thing at time -5?
I just did negative 6. Negative 2. Negative 1. Negative 2. Negative 3. Negative 3. Negative 3. No, positive 3. Positive 3. It's positive 3.
6 times 5.
Are you sure that that's your sixth and final answer?
Yes. Positive 3.
It's positive 3. It's 1.
There you go. It has to be right enough.
Positive 3 is what I'm negative. Go at time -6.
Positive 8.
Positive 8.
Yeah, the boys.
At time +1.
8. Positive
Plus 6. It's 6.
8. Positive.
8.
10. Positive 8.
What'd you get?
Oh, no, minus. Never mind. Never mind.
I'm just putting 1 into these.
No, I times them.
1 + 2, 3. 1 + 4, 5. 3 times 5. That goes. Alright. So, we've got some more points on here, so that might help us to figure out what's going on. Another thing that might help you to figure out what's going on, draw some sort of dimension. That's supposed to be straight. This is my X dimension. This is going to be 0. This thing goes to infinity on everything, but I'm going to make this -15 here. -10 there, -5 there. Okay. Where does this thing? Sorry, let's just take the time interval from -6. So time is -6. Where do we start?
Positive 8.
Okay, positive 8. So we're starting somewhere around here.
Yes.
Okay. Next position.
Negative 5.
Okay, -5 goes to 3. So where am I going?
In the negative direction.
Just drop it.
Gone.
Right, so we're at time -5, we're up to 3 as a position.
Gone -5 spaces to the
Cool. So I've gone that way. Yes? Cool, okay. Next time is -4. What happens?
It stops at 0, goes to 0.
Okay. So I'm going to there. Cool. So that's the purple.
No.
Next colour, blue, does this.
Goes to -1.
Okay.
It does a little
Tiny little bit. Next thing that happens.
It goes to 0.
back to 0.
Then
It goes to 8. I'm 3 first, it goes to 3.
right, goes to 3,
I didn't see that.
and then
And it goes to 8.
go.
And then 15, and then. Oh, wait, no, it just goes to 15 for the start.
Yeah.
Nice.
Each of these intervals, keep in mind that this is one interval, that's another interval. How long is each interval in terms of time?
So then
1 second.
1 second. Right? So it covers this, so it goes 1, tick, tick, 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 1, tick, tick.
Wait, how do you
How?
know that's the speed? How do you know that's how fast it's going?
Measured.
Or how do you know each interval is 1 second?
We did each of these is 1 second apart. Yeah?
Oh, okay, yeah.
Okay. So we're starting at time -6, whatever that means. And then we end at time +1. Okay, fine. How is this object moving? Forget negative and positive for a second. How is it moving?
Define how is it moving?
If you saw an object do this movement,
Forwards and
what would it be doing? Right, forwards and backwards potentially? Yeah?
Forwards.
Forwards and backwards or backwards and forwards?
Forwards in a positive direction.
Backwards and forwards.
in a
Backwards
negative
and
direction.
forwards. Right, it's going back, it's going to
Oh,
the negative
yeah,
direction
right.
first and then going positive. Yeah?
Hmm.
So this thing is going backwards and then eventually starts coming forwards. Does it do that all at the same speed?
Yes. No. It does that in the same time interval, but it does it in the same. It does it in the same time, but doesn't do it at the same speed.
Okay. Each interval is the same amount of time, true. At any point from here to here, is it going the same speed?
No.
No, what's it doing?
Slowing down.
Thank you, that's what I want. It's slowing down. Right? If it's slowing down, it has a negative acceleration. Okay, great. So it has a negative acceleration for that leg. What happens here?
It has a positive
It's
acceleration.
simultaneously
Right, for a moment it's stopped.
Oh, yes.
Alright? So it's stopped just there, then what does it do?
It accelerates.
It accelerates in the
Positive direction.
positive what direction?
Positive right direction.
Positive right direction?
Positive
Positive x direction.
Positive
Oh, nice.
Right? Because this dimension was x. So I've written the x dimension this way, but on the graph it's this way. Right, cool. What's it doing? Speeding up, right? Accelerating, great. Does it ever stop accelerating?
No.
No, it just gets faster and faster.
So,
No.
can you just literally just turn that graph sideways and then just look at it from there?
You can if you want, so there's going to be a slight problem because then time will now be pointing down, right? But x would be pointing out that way. So that means that now you have to follow your graph down. So this thing, which would actually be like this, it would be, yeah. So you have, hang on, I'll draw it on this. So that's the same axis on here, so that's now x. Where this is negative, that's positive. This is now a positive time. And so I get, except this is time 0, 0. Wait, is that right?
No, I just mean like the x on the right side and t on the down on the bottom.
That's what he's just done.
Like he's flipped it this way. Yeah, but look. That's very
What? Except I need this x axis here. started in negative time. So I get something like that. And then I've got purple to there, blue to there, green to there. My curve's a bit bad, so that should actually be there. And I guess so my x-axis should actually be a bit lower. Should be around. And this is 2 purple. So there you go. Okay. Is that helpful?
No.
No, right? It doesn't matter what you do. Right? You're going to have to think it through bit by bit. Interestingly, in particularly particle physics, you have time going up and your spatial dimension going that way, and then you imagine things moving through time that way. But you can actually have things that move backwards in time as well. So yeah, it doesn't matter. It's just a math trick.
But will they give you an idea of what the graph would look like if they give you a function?
So
So would they give you an idea of what
with this,
that time graph on the top?
what does this do?
No, like would that bottom graph allow you to have an idea of what that top graph would look like?
Potentially, if you want to do it that way, but you're almost certainly asking for trouble because now you've shifted everything. You've rotated it, which isn't normally how you draw these things, because now you're drawing relations instead of functions.
And what if you draw that one first and then you're just like if I want to...
I would definitely draw this one first.
Yeah.
Always. Right, because this you're used to being drawing functions. So all of your intuition is in here. And then from there you have to extrapolate, okay, what's actually this describing? Cool. So we're all happy that this thing's, depending on where we pick as our starting point, it's moving to the left slower and slower and slower, then spins around and moves off faster and faster and faster.
Yeah. It's like a boomerang.
Sure, why not? Now for the next thing, if I start this thing at time is -6, what does that mean?